Hello, this is the project video from Team 29. Our project title is 3D Spaces from 2D Images, and our client is Fergus Kidd from Navanad. Due to the pandemic, the demand for remote meetings rises rapidly. Meetings through VR might be a new and effective way. There are technologies or platforms such as Microsoft Mesh that helps the growth of VR. However, if we want to further popularize VR, user-created content will be pivotal. Now the problem is, the 3D models are usually created by skilled 3D model artists with specialist software like Blender. 3D modeling is too hard for common users. We want to find a way to simplify the process of 3D modeling. According to the client, we want a way that a user with little or no experience with 3D modeling could upload their own real-life photographs and get the 3D models they want. After the meeting with the client and the analysis of user requirements, we summarized 3 key requirements of our project. Research various techniques that exist to convert 2D images to 3D models. Evaluate the techniques to see the current state of such technologies. And then create a demo as a proof of concept of a tool to convert 2D images to 3D models. Our current deliverables are a report summarizing various solutions for the 2D to 3D conversion problem, and a usable demo that implements one of the solutions.
As our project was research-oriented, we have looked through multiple algorithms and solutions to a 2D image to 3D object problem. Here are some solutions in a taxonomy map categorized. The main distinction is the single view and multi-view. Single means solutions can only take one image as inputs, and multi takes multiple pictures as inputs. In addition, with software-based solutions, we also have a hardware-based solution which utilizes the Azure Connect camera and its LiDAR sensor. Another distinction between the solutions are the outputs. We identified multiple output types. Voxel, which are objects made out of essentially 3D pixels. Meshes are 3D objects built from polygons. Point clouds are set of data in a 3D space making up an object. And lastly, occupancy network that uses a neural network to approximate 3D points. For our demo, we use a model view controller design pattern. The model will directly interact with 2D image to 3D object solutions. The user will input an image and that will be passed from the view into the model so that the solution has an input to generate the 3D object. To create a demo tool, it was necessary to have a toolchain. First, we took the source code of a 2D image to 3D model converter written in Python. We then used PyInstall to convert the source code with its dependencies into an executable. We will then implement the executable into our GUI. Our demo tool is a GUI written in PyQt5. It implements one of the solutions that step for its 3D object generation. The demo tool takes in a 2D image and will output a 3D model. The generated 3D model can then be visualized using Open3D and can be saved in the user's desired directory. Here we have a demonstration of our demo tool. I'll first get a 2D image and I'll drag it into the box. I'll now convert the image. It'll take a few seconds. I can now visualize the generated 3D object. Users can save the 3D object using a save button to their desired directory. The demo tool only implements DenseF solutions so far. However, a demo tool can be easily expanded to include more solutions as long as an executable can be generated from the source code.
Our report covers all of our research into 2D to 3D converters. For each one, we cover a summary of what it does and how to install or set up the solution, show the possible inputs and output of the solution, including a graphical representation of the conversion process, and then an evaluation of the solution. So the evaluation itself is split into 2 parts. The first is an evaluation of the installation process and how difficult it is to set up and use, as well as the use cases for the solution. The second is an evaluation of the solution's speed and performance. So the solutions that we focused most on in research are the DenseDepth and 3DR2N2, and we'll also be focusing mostly on those in this presentation as well, though we did cover others that all cover different kinds of use cases, have different outputs and such. For testing, we primarily use the ShapeNet core database, which is a database of 3D shapes covering 55 different object categories. So this is an example of input data. We have the image of the birdhouse and a corresponding ground truth model. Other datasets are also used, such as the NYU Depth Dataset version 2, which is a dataset of indoor scenes, just generally. Additionally, some of the performance evaluation that we've cited also uses the Kitty database or dataset. This is more focused towards autonomous driving, but it was still used in some of the papers that we've cited. So, our testing had some of our own results as well as results from other comparison studies. So for our own testing, I made an easily extendable design where each solution is an object that can be passed into a test object. Testing was focused on dense depth and 3D R2N2, so they were well documented, easily installed, and covered 2 interesting use cases. The ShapeNet dataset was primarily used for our own testing. So I'll summarize the main solutions that we researched. So the dense depth algorithm takes a single input image and outputs a colored 3D point cloud that is a depth map of the original image. The use case with this would be like if a user wanted to scan a room to be the background of a virtual space, for example. However, unfortunately, it produces a point cloud, which means that more processing will be needed to convert it into a model that can be used in something like VR. But it is absolutely possible using something like a deep marching cubes algorithm. Across multiple categories of image, on average it took about 40 seconds to convert an image into a depth map on a regular home PC. Compared against other depth estimation algorithms, it wasn't the fastest, 0.35 seconds compared to the fastest being 0.22 seconds. However, generally the speed was comparable to other similar algorithms. The same was true of performance, so the absolute relative error was 4th out of 13 different state-of-the-art solutions that were compared. So 3D R2N2 can take one or multiple images of an object and convert this into a 3D voxelized model. The proposed use case for this would be if a user wanted to scan an object into a VR environment. As it produces a voxelized model, no further processing is needed. This can be imported straight into 3D modeling programs. However, on average, it takes significantly longer than dense depth, about 100 seconds on average per model across multiple different categories. However, overall, compared with other single image reconstruction algorithms, comparison studies have shown that it has a comparable performance, though unfortunately, visually, it might not look as good due to the fact that it produces a voxel model, meaning just visually it looks blocky compared to something like a mesh or a point cloud. So overall, we have researched multiple 2D to 3D conversion methods and written a report detailing all our findings. We've created a demo tool that converts a user input image into a 3D model in a user-friendly environment. So here are our references, and thank you.